Okay, so welcome back. We are currently working through lecture set number 4, which mathematically is a fairly involved lecture set. And I actually realized last class that when we got to the end of the proof for the sampling distributions for the MLE, I made a mistake in this area here that I'm going to address today. And essentially, like the issue is the starting point here where I have find the expected value of the score. This is clearly, or this is a kind of a ridiculous statement because we know the expected value of a score function is 0. We've already proven this on several occasions. And so having this written here is automatically ridiculous. And the other issue is we're not looking for the expected value of the score function of beta. We're looking for the expected value of the MLE. So this exercise is about deriving the sampling distribution of the MLE because we want to be able to conduct inference about our model parameters later. So this whole exercise is basically about showing that the MLEs for a GLM are normally distributed. And as we will see later on, the result of that is when we go and actually conduct inference, we can pull information, or the standard errors and the estimates that we see in our output are going to be normally distributed. And that's why we have a Z-score attached to them. So we need to fix this up. Now, bits and pieces of what I wrote here is true, which is helpful. And what I'm going to try and do now is just kind of clear up this section so that we can get the expected, so that the solution ends up being what's shown here. And then on the next slide, we already have shown the variance covariance matrix for beta hat. So we'll come back to that in a bit. And then we will, we'll just move forward and look at a few illustrative examples. Okay, so I'm just going to push this part down for now. And I'm just going to make a note. So this is going to be January 27th. Errata. Okay, so first off, this part here, we want the expected value of beta hat. Okay. Or the expected value of beta hat. Actually, let's just use the multivariate one because that's how I end up proving it anyways. Okay, so we're going to take this. We want the expected value of this. And we want its associated variance. Okay, so that's the first thing. What we're actually looking for is the sampling distribution of beta hat. So we need to work out the expected value of beta hat and the variance of beta hat. In this case, beta hat is a vector, so we're going to be looking for the variance covariance matrix of beta hat. All right. Now, what we were going to say is, so we have the score function around the vector beta is equal to S of beta hat, is equal to S of beta hat minus the information matrix at beta hat multiplied by beta minus beta hat. Okay, so that's in the red box right above my January 27th line. Okay. All right, so let's call this equation I don't know, call it 1 maybe. Wouldn't really be in line with what's given though. I'm just going to write from above. Okay. So I'm going to move this out of the way for now. And I'm going to bring these back momentarily, okay? Okay, so this part here is true. Okay, so by definition, beta hat is an MLE. So it maximizes the likelihood and is the solution to S of beta equals 0. Therefore, S of beta hat equals 0. Okay, so therefore, the expected value of S of beta is equal to this. Okay, so what I'm doing here is I'm just saying I'm taking the expected value of the equation in the red box above the January 27th note. And I'm saying, okay, well, since S of beta hat is equal to 0, the expected value of S of beta is equal to the expected value of the negative information function times beta minus beta hat. All right. So, okay. And now what we can do is we can just start to work this proof down. So then we say, if we treat the negative information function as a constant, okay, then we have from above 0, because we know the expected value of the score function is 0, is equal to negative I beta times the expected value of beta minus beta hat. Okay, which means that 0, because the information function is being treated as a constant because it's evaluated at beta hat, this is equal to the expected value of beta minus beta hat. Okay. Therefore, the expected value of beta hat is equal to beta. Okay, there we go. So that was the mistake I made last time. In the original solution, so when we were working through it on Tuesday, I kind of did this weird roundabout thing where I ended up showing the expected value of, like, I used the result that the expected value of beta hat is equal to beta to show the score function was 0, but we already know the score function is 0. That's by definition. And we're not trying to find the expected value of the score function. We're trying to find the expected value of the MLE, because what we're trying to do here is show the sampling distribution of the MLE so that we can conduct inference about the model parameters later. So the result is that the expected value of beta hat, the vector, the MLE, is beta, which follows from our work with the normal regression model anyway. So this is something that we probably expected to be true, but we still needed to show it was true in the context of like we'll call it open or undeclared generalized linear model. Right. And then from here, the next proof follows directly. Any questions about that? Okay. All right, so we have, now that we have completed this, we can show that for the vector beta, okay, the sampling distribution is chi-square on P, which represents the number of parameters in the data set. And we call this the walled statistic, right? And then in the one parameter case, we have beta hat is normally distributed with mean beta and variance given by the information function. Okay. So pretty nice result, basically showing that the model parameters given the results that we have shown before for the exponential family members, they are also normal, which makes conducting inference, very straightforward because we know how to work with the normal distribution. Okay, what we're going to do now is look at a couple of applied examples. So these are going to draw on some of the proofs that we have in lecture set number 3, but I'll try and simplify it as much as possible. Okay, so first thing, let's consider the normal linear model. So we have the expected value of yi is equal to mu I is equal to xi transpose beta, where the yi are normally distributed with mean mu I and variance sigma squared. We want to show that beta hat minus beta transpose multiplied by the information matrix times beta hat minus beta is chi-square. Okay, where just for clarity here, the J is the information matrix for beta hat. Okay. All right, so first, since the link function is the identity mu I is equal to eta I, and d of mu I by d of eta I is equal to 1. Okay. All right, so therefore, J by ik is equal to the sum from I equals 1 to little n of xi xij xik over the variance of yi. which means that j is equal to x or 1 over sigma squared x transpose x. Since the variance of yi is equal to sigma squared. Okay. Further, okay. So then we can say, where is that? Okay, so further, the estimating equation given here is going to be equal to the sum from j equals 1 to p of the one plus I minus the sum j equals 1 to p one, which is equal to y. Right? Okay, so for the normal linear model, obviously the simplest case, so we're getting a lot of cancellation here. So from lecture set number 3, when we drove the estimates and the corresponding, or when we drove that iterated weighted least squares method, we talked about the derivation of the expected value of the information function. So that's what this first matrix here is. So we're showing that the information function is just 1 over sigma squared multiplied by x transpose x. And then in the second line, we're saying, okay, here's zi, that estimating equation from lecture set 3. I'll have to go back and review this, but the general form is given in the first line here, right? So this is the open form. Now what we're saying is the derivative here is going to be equal to 1. So we can replace this with a 1. And then we have that mu from the model stated above is also going to be estimated by the sum of xij times the beta j. So therefore, this portion cancels out. We multiply by 1, and now we have the zi is equal to yi. All right. Okay. So therefore, so it follows that in this case, 1 over sigma squared x transpose x, or rather, we should write it this, okay, follows that x transpose x w times beta hat on iteration k equal to x transpose w z can be written as one over sigma squared x transpose x beta hat k is equal to 1 over sigma squared x transpose y, which gives beta hat k is equal to x transpose x inverse x transpose y. Okay. Since the linear, we'll call it the normal linear model, can be written as y is distributed normal x transpose beta sigma squared I okay, then the expected value of beta hat k. Actually, in this case, we don't even need to iterate it. So we don't need the k's here. This is going to be closed form because in this situation, the values don't depend on beta. Well, no, this will be a closed form exact solution because of the model we're dealing with. So then we have here the expected value of beta is equal to the expected value of x transpose x inverse x transpose x beta, which is equal to beta, right? Which is what we would have expected. And then we can say, and the variance is found using beta hat minus beta is equal to x transpose x inverse x transpose y minus beta is equal to x transpose, Therefore, the expected value of beta hat minus beta multiplied by beta hat minus beta transpose is equal to X transpose X inverse X transpose times the expected value which is equal to X transpose X inverse X transpose times the variance of Y X X transpose X inverse, which is equal to sigma squared. So bad at spacing stuff. All right, and then we can say, since the beta hat is a linear combination of normally distributed random variables squared, or no, sorry, mu I sigma squared, right? Then the beta hat are also normal, and we can say that that's beta hat minus beta transpose J beta hat minus beta distributed chi square. Lots of proofs. All right, I'll give that a few seconds. Let me know if you have any questions. Okay, so we started off the class reviewing the derivation of the sampling distribution for the MLEs, right? So we made those corrections and we showed, okay, the expected value of beta hat is beta. The covariance matrix or the variance of beta hat is the information function. Fairly basic definition, right? And then the distribution or the isotopic sampling distribution is then chi-square. And we call this the Wald statistic. Okay. Now, the illustration that we just worked through in the case of the normal linear model was essentially just an example of how we can derive the same result in a very simplified case, which is the case where the response variables are normally distributed. And we can show that through the GLM estimation scheme that we derived earlier, we end up with the exact same result that we would find if we had just started or if we had solved directly using the properties of the normal distribution. So this result is something that we would have seen before back in Stat 378 when we were introduced to MLR models. Okay, what we're going to do now is use the result that we started the lecture with. So the general result for the sampling distribution of the MLE from the GLM to derive a model validation criteria. Okay. Okay, so when we work with generalized linear models, we define the maximal model or the saturated model, same thing, as the model with one parameter for each response variable. So this is like, you know, the full model, the biggest possible model you can have for the data set, hence maximal or saturated. Right. Now, if we have replication among the n observations, then the maximal model will have a number of parameters equal to the number of unique values in the data set. So if we let little m be the maximum number of parameters that can be estimated, so you could think of little m as the number of unique values in the data set, then beta hat max will be the MLE for beta max. Okay, so for the saturated model, the likelihood at beta hat max is going to be given by L of beta hat max, right? Okay, and this value should be larger than the likelihood for any other model with the same link function and distribution for the response. Okay, so we're always going to be comparing models within the same family is the point. So the maximal model evaluated at the likelihood for the fitted model evaluated at beta hat for the maximal model will be larger than the likelihood for any other MLE of a subset model, given the same family and the same link function. Any questions? Right. So let L of beta hat be the likelihood function evaluated at an MLE for some other model. Okay. So the likelihood ratio is given by the following. Lambda is equal to L of beta hat max divided by L beta hat. Okay. So lambda provides a statistic for evaluating the fitted. Actually, I'll just say, yeah. For evaluating the fitted model. All right. In practice, we typically use the log of lambda to evaluate the fitted model. Right. Okay, so basically what we're saying here is the likelihood ratio is the ratio of the two likelihood functions. In practice, to evaluate the fitted model, we can use the log of the likelihood ratio, which is now the difference between two log likelihood functions. So rather than dividing the log likelihoods, we can just take the difference between the two log likelihood functions. Right? It should be the same result, but computationally a little bit simpler. All right, so then we can say large values of log lambda suggests that the model of interest is a poor description relative to the maximum model. All right. Now, the question then becomes like, what does it mean for log lambda to be large? Well, okay. Well, to answer this question, we can say it has been shown that 2 log lambda follows a chi-square. Okay. Therefore, we can compute 2 log lambda and compare, and this is on df, and compare to a chi-square df. The value 2 log lambda is called the deviance. Oh, look at that. I had that typed out on the next slide. Oh, that's embarrassing. Anyways, all right. Well, just wasted a bunch of time. Okay, so we have, in practice, we typically use the log lambda, which is the log of the likelihood minus the log of this. Large values of log lambda suggest that the model of interest is a poor fit. What does it mean for the value to be large? Well, it's been shown that 2 log lambda is chi-square, so we can use 2 log lambda and compare to a chi-square distribution. We call 2 log lambda the deviance, and then I have this repeated here, so I didn't need to write all that out. Ugh. How embarrassing. Okay, anyways, moving on. I'm gonna just very quickly make sure I'm not, okay, deviance, and then an illustration. Sorry about that. Obviously too caught up in writing out examples now. Okay, so we have 2 log lambda, which we call the deviance. So we can say that the deviance, which we'll call capital D, is 2 log are 2L beta hat max minus 2L beta hat. Since the MLE of beta is beta hat, then L beta minus L beta hat is equal to -1/2 beta minus beta hat transpose multiplied by the information function at beta multiplied by beta minus beta hat. Therefore, two L beta hat max minus L beta is equal to the following, which we know is chi-square p. This result, we can show that D is equal to 2 times L beta hat max given Y. It's L beta hat given Y, which is equal to 2L beta hat max given Y minus L beta max given Y minus 2 beta hat Y minus L beta given Y plus 2 L beta max given Y minus L beta given Y. Okay. Okay. Since So since the first term will be chi-square p, the second term will be chi-square m. And the last term, which we can designate nu, will be approximately equal to 0. Then the deviance is going to be distributed chi-square on m minus p and nu. Nu is a non-centrality. It would mean, that's a good question. In the case of the chi-square, it would control so the non-centrality parameter. So the chi-square is a right skewed distribution, and the non-centrality parameter essentially causes it looks like it also controls the shape. So it looks like it causes it to skew out more as it increases based off these illustrations here. So one sec, I'll just show you what I mean. So I'm gonna stop this one. And then I'm going to share this screen here. Okay, so this is an illustration given from Wiki. And here we have lambda is the non-centrality parameter and k is the degrees of freedom. Okay, so you can see the first 3 lines here, those are all for k equals 2 degrees of freedom, and then lambda is increasing. And you can see that as lambda increases, the peak comes down and then the tail shoots out more. And then when k is equal to 4, it looks like the same result. So it seems like what the non-centrality parameter does is it would almost like push the mean out away from 0 because the skewness is or the tail is elongating. So that would, yeah, as a result, it would kind of cause the mean to get pushed in the positive direction as it increases. And then the result of this would most likely be the higher the non-centrality parameter, I would imagine it would then become more difficult to reject the null hypothesis, because for a fixed significance level, the value is going to get pushed further out. a good question. All right, so turn this off. All right. Any other questions? Okay, so for each of the different models that we're going to discuss in the class, the form of the deviance is technically different, or is different. The deviance is a value that is automatically outputted for us in R. So it's a value that we can actually confirm, and we'll work. We'll see examples of confirming the values in later assignments. But for each of the different response variables that we can consider, we can compute a different deviance. So for example, in the case that we have our response variables being binomially distributed, then we can show that the deviance for this set of random variables can be found as follows. Okay, so first, just a reminder that if we're working with a binomial random variable, then our density will be given by ni, yi, pi I, yi, 1 minus pi I. Yeah. To the ni minus yi. Okay, so then the log likelihood function for beta okay, so then we can say the log likelihood function for beta given y is going to be equal to the log of the likelihood, or the log rather, of the product from I equals 1 to n of f of yi. Okay, and then this is going to be equal to the sum from I equals 1 to n of yi log pi I minus yi log 1 minus pi I plus ni log 1 minus pi I plus log n. Where beta is equal to pi 1 to pi n transpose for the saturated model since the MLE for pi I is given by pi I hat is equal to yi over ni, then the log likelihood for the saturated model is given by L beta hat max given y is equal to the sum from I equals 1 to n of yi log yi over ni minus yi log ni minus yi over ni plus ni log ni minus yi over ni. Okay. And then we can say for any other model with p less than n, pi I hat is the MLE for pi I, and yi hat equals ni pi I hat are the fitted values. Therefore, the log likelihood, okay, so therefore the log likelihood for these models is given by L beta hat given y is equal to the sum y equals 1 to n of yi log yi hat over I minus yi log ni minus yi hat ni plus ni log ni minus yi hat over ni plus log. My hand. Okay. therefore the deviance is given by d equals 2 times. So 2 times the log likelihood at the saturated model minus the log likelihood of every other model. So this is going to give us 2 times the sum I equals 1 to n of yi log yi over yi hat plus ni minus yi log ni minus yi over ni minus yi hat. All right. Any questions? Okay. All right, another example. So we're going to do 2 more examples of deviance calculations. So we'll do one for the normal and one for the Poisson. Maybe a bit overkill, but these are the main models that we're going to be working with in the class, or at least for the next few weeks. So I think it's useful to be able to see where that deviance measure comes from. And then it'll give us the ability to actually verify output once we study implementation of these different models in R. That being said, we'll look at the normal in small detail. We're not going to spend a lot of time on that model because it's something that we studied a fair amount before. But we'll look at the deviance calculation anyways. We'll talk a little bit about output from that model in a lab, probably not next week, but maybe the week after. And then we will, as I said, we'll verify the output using the calculations that we've done in lecture. And then we can do this for the binomial and the Poisson as well. So again, just helping us understand like where the values in that output is coming from, how the models are fitted. You know, all this background work is meant to build up our understanding of what the processes that are actually taking place kind of behind the R function, if you will. Okay, so deviance for the normal model. It's a very similar starting point, right? So we have to start out basically by finding the likelihood for the saturated model, and then we'll find the likelihood for every other model that we might fit. And then we're going to take the difference between them. Okay, so in this situation, again, we'll just start off with a quick reminder. So f of yi is going to be 1 over the square root 2 pi sigma squared. Okay, multiplied by exp negative 1 over 2 sigma squared yi minus mu I squared. Okay, so for the saturated model, mu beta equals mu1 to mu n. So through previous calculations, well, that wouldn't exactly be true. So sorry, not through previous calculations, but so following the process for deriving MLEs, we can show that mu hat I is equal to yi. Okay. Therefore, L of beta hat max given y will be equal to -1/2 sigma squared times the sum from I equals 1 to n of yi minus mu I hat squared minus 1/2 n minus n/2 log 2 pi sigma squared is equal to -n/2 log 2 pi sigma squared. Okay. Pretty nice simplification there. And embedded in this is a little bit of an exercise for you to work on. So you can take, you can show that the mu I in this case is going to be equal to each individual point if we have a mu I for each point, following from what's given above, or following the process for deriving MLEs. Okay. So for any other model, oh, sorry guys, I'll be right back. Okay, for any other model, okay, with p less than n, let beta hat equal x transpose x inverse x transpose y, then L of beta hat given y is equal to -1/2 sigma squared times the sum I equals 1 to n of yi minus xi transpose beta hat squared minus n/2 log 2 pi sigma squared. therefore the deviance is given by I guess right here, D equals 2L beta hat max given Y minus L beta hat given Y equals 2 equals 1 over sigma squared times the sum I equals 1 to n yi minus x equals 1 over sigma squared sum I equals 1 to n yi minus mu I squared. Where mu I hat is a fitted value from xi transpose beta. All right. Okay, I'm going to stop here for today. It's a lot of work. All right, so making progress. We're almost through this lecture set. We should be able to start lecture set 5 on Tuesday, which is going to be on, most likely it'll be on logistic regression. Maybe I'll put a short lecture set together about the normal linear model, so we have kind of like a control or a context to talk about it in, but I'd rather just kind of push ahead into the next topic, which is how I scheduled the course. So I think on Tuesday, we'll probably be able to start lecture set number 7. We have a couple more examples left in this set. So we're going to do the deviance calculation for the Poisson. Then we'll look at an empirical example where we actually compute the deviance and we use it so that we have an illustration of how we would actually use it in practice. And then we have one more example where I want to show using the deviance measures to compare two models within a hypothesis testing setting, but compare two non-maximal models, because the deviance kind of is an automatic comparison of the fitted model to the maximal model, but it's also useful to be able to compare two models that aren't the maximals to one another. Okay, and then a reminder, so we have the first quiz next Thursday, which will be online from 11 until 12:20, so during class time. I'll send out a reminder and some details about that soon. And we'll do review for the quiz in the lab next week, because there won't be any actual R components for next week's lab. So that works out pretty well in terms of preparation. Okay, I think that's it in terms of announcements. And if you guys have any questions, I'll hang around. And otherwise, have a good weekend, and I will talk to you on Tuesday.